capstone, I guess that's not an option.
What's that?
So if you're taking capstone, I guess.
No, it is. It is because we're not doing the capstone presentations till that afternoon. I can't be in two places at once, so. Like for me, I have to do the exam in here at a time slot that I can also do the capstone presentations because I can't be in two places at once. So if you wanted to do the steel design exam and then the capstone presentation, you could. And so probably what I will do for capstone, I haven't formalized this, but it'll probably be at 1 on Wednesday, from 1 to 3. I like how I drew this graph on the board, by the way. I'm going to do this better. This sort of trails more upwards than I would like. Okay, everybody, let's get started. All the outstanding homework's been graded. There's no homework due today, but we do have a homework assigned today. Okay? So I will go ahead and tell you we are basically going to have homework every day for the rest of the semester, other than I'm not assigning a homework next Friday. Next Friday is our exam review session, and I'm not going to assign anything for that. But you're going to have a homework due Wednesday, one due Friday, one due Monday, one due Wednesday, and one due the following Friday. So I'll say that the latter 2 assignments are really short. And if I'm being honest, I don't really think these assignments are too long. I think they're pretty straightforward. There is some formula manipulation that's a little wonky for this assignment coming up, but that's kind of the purpose of today's lecture. Don't forget, you still have the bonus course eval assignment. If you haven't already done your course eval, if you upload proof that you did it, I will add 10 points to your homework average. Don't forget that Friday we are not meeting in person. I've already pre-recorded that lecture. It will go live Friday at 11, and then that'll sort of make up for us missing for the Virginia's conference. Because I'm sort of planning on kind of being around and helping stuff on Friday. At a minimum, I know I'm going to be helping set up the steel bridge competition. So like setting up the lanes and all that. So I just went ahead and pre-recorded that. Okay, any questions? All right, okay, so today what we're going to do is discuss, we're going to continue our discussion of analysis for lateral torsional buckling. If you recall, what we left with was last time was this. This was our flow chart that we developed, and the flow chart essentially is just this right here, this plot, represented in equation format. So what we do is we determine what zone we're in. Based on that zone, we can compute the capacity. We've already done zone 1 problems for a long time now. I mean, that's what the plastic moment, that's what continuously braced beams are. It's just BMP. Zone 2 is what we did last time, and so today we're going to have an example on zone 3. Now, one note I did want to mention, and this is kind of important for a conceptual understanding, is a note on LTB analysis about a beam like this. Okay, so this is a more intricate beam. There's a lot going on with this problem. So if you look, I've got a beam that's overhanging, and if you notice, I've got 4 braces. So this creates 3 unbraced segments. For each of these unbraced segments, I could have a different LB, I could have a different CB, and I could have a different maximum moment within that segment, okay? And so I'm just using this as an example that in general, you could have a beam where there's multiple segments that this is the case, okay? So if each segment has a different LB and CB, then each segment has a different VMN, and each segment has a different MU max, okay? So for analysis, for evaluating that beam, you need to check all of them, okay? So what you need to do is draw the factored moment diagram for the entire beam, compute the VMN for all the segments, and basically compute an efficiency or a performance ratio for every segment. Now, which one that governs is the one that has the largest performance ratio or the largest efficiency. But from an analysis standpoint, you need to look at all of them. Fortunately, and in reality, most engineers try to exploit symmetry. So they try and look at problems that have symmetric bracing and symmetric loading and things like that to where you can avoid having to check all of them. but it's not unreasonable to have a beam where you might have to check 2 unbraced segments. That's not outside the scope. For shears, just use the maximum shear overall, unless the shears get really, really high, but that doesn't really happen too often in building design. And for deflections, just use the maximum deflection. Okay, what I want to do is sort of close the loop on computing capacity, and I want to look at a problem that's ultimately going to be a zone 3 problem. So I want to look at a W14 by 61, and I want to determine the flexural capacity for these situations here. So I want to look at it if we have A992 steel. I want to look at it if we have an unbraced length of 30 feet and we have a moment gradient modifier of 1.5. Now, one thing I'll mention here, and let me pull this up. Here. One thing I'll mention about this problem is that in order to do this problem, we're going to need to look up several properties in Table 3.2 in the ZX charts. And I'll go ahead and tell you that the W14 by 61 is not one of the bold rows, okay? I'll tell you that right now, it's not a bold row. And there is a reason for that, okay? I want you to be able to get used to looking through W14 by, or looking through Table 3.2 for sections that are not bolded, okay? That might not make a lot of sense right now. It will later, and you'll see what I mean. So we've got A992 steel, which means we can use Table 3.2 to look up LP and LR and things like that. Let's go ahead and do that. Let's go to the ZX tables and let's see if we can find the W14 by 61. So let's see, for that W14 by 61, if we can start to glean some data from this section. So specifically what I'm after right now, let me be clear, is I want to determine the zone. So I need the LP and the LR for the W14 by 61.
LP is 8.65.
Okay.
LR is 27.5.
Okay, so let me write that down. So 8.65 feet and 27.1 feet. Is that what you're 27.5 feet?
27.5, yeah.
Okay, and just to make sure that everybody's on the same page, literally. So page 3-25, and I'll put lowest group, and we'll say the third row. Is that fair? Like, is that a good way of describing it for your notes? So, now, what does this mean? What is our LB for this problem? So our LB, get ahead of myself. We were given as 30 feet. So we are in zone 3. Okay? And just to make sure that we're clear, what we're doing is we're looking at our LP and LR. In this case, LP is 8.65 feet for this section. LR is 27.5 feet. And we have an LB of 30 feet, so we're over here in zone 3. Is everybody okay with that? Okay. So in order to compute the capacity, let me kind of make this a little easier to navigate here. So let me scroll down. So here's the flow chart. I thought, what the heck? Let's just put it all here in the notes so that they're all there. So we have zone 3. So in order to compute the capacity, we first need to compute this, okay? And then we'll go through and compute phi-mn. So this is a little bit of an involved expression, and unfortunately there's no way around it. Like if you remember the LR equation was kind of nuts, but we don't ever have to really compute LR because we can just look it up. But this we can't really look up. We have to just get through it, okay? So in order to compute the capacity, we're going to need a few things. So let me scroll down here, and let's look at zone 0.3 elastic LTB capacity. Okay, so we're going to need our CB value, which we were given our CB value. Our CB is 1.50. Okay, so let's just go through actually the equation. So we're computing FCR equals all of this. Let's just start writing down everything here and let's see what we need. So we've got, let's see, CB, pi squared, we know pi, E. We need E. E is 29,000 KSI. We do need LB. LB was in this problem given as 30 feet, but I'll go ahead and tell you we need to go ahead and convert that to 360 inches, okay? And everything else that we see here is a section property for a W section. So what we need is we need RTS, we need J, we need SX, we need H naught, okay? And all of this, we can get this from table 1-1. So somebody help me out. We're looking at a W14 by 61. What is RTS? So RTS is a radius of gyration for lateral torsional buckling. So it's in inches.
2.78.
2.78 inches. What about J? J should be a really tiny number. 2.19. 2.13 or 2.1 what?
9.
2.19 inches to the fourth. What about SX?
92.1.
92.1 inches to the third. And then H naught. H naught should be close to 14, but a little less.
13.3.
13.3, sounds about right. H naught is the distance from the center of the top flange to the center of the bottom flange. And so if this is a W14, it should be a little less than 14. So if you look at all the inputs, everything's in inches except for LB, so that's why you got to go ahead and convert LB. So like I said, this equation, it's kind of long, but let's just get through it. So therefore, FCR is CB pi squared E over LB over RTS squared, and then 1 plus 0.078 JC over SXH naught LB over RTS squared, and then the square root of all of that. So equals, okay, let's make this as neat as we can. So 1.50 pi squared, 29,000 KSI over. Then we have 360 over, move this over here. So 2.78 inches. Okay, and I'll do that square root later. So 1 plus 0.078. Need some brackets here. So 2.19 inches to the fourth, 1.0, and then 92.1 inches to the third, and then 13.3 inches, 360, 2.78 squared. Oh, squared. Don't forget to square the L over R's. Okay, and then square root of all that. Okay, this is definitely one that I think that everybody in here should break out their calculator and try and do, because this is not outside the scope of possibility for homeworks and exams. And so this is a long formula. This is probably the longest formula in steel design. that you actually will probably do. So I want to make sure that you all are getting the same answer. And whenever somebody first gets an answer, go ahead and shout it out. We'll do like 3 decimal places for this because I want to make sure everybody gets the same thing. That's just for your all's sake. Okay, 28.44, that's not what I got.
Got 46.78.
Something, or 779, something like that.
Yeah, 779.
Check your squares. Make sure that you're squaring your L over R's. Now, one of the things that's worth mentioning is I just sort of said, oh, that's KSI. If you notice, what's actually driving the units on this calculation is that. Because if you look from left to right, inches over inches cancels. Okay? What about inside the square root? What about inside this brackets? Inches to the fourth, inches to the third times inches. Everything in here cancels. Inches over inches cancels. Everything inside this square root is unitless, and everything down here is unitless. The only thing that drives the units is that. So that's why the answer is in KSI. Right. And so for this part right here, make sure it's 1 plus all of this is one big product. So, were you able to get yours?
Yep.
Okay.
An extra 0 and 0.0078.
That'll do it, yeah. Anybody else? Everybody else able to get this? Okay, all right. Just make sure you're comfortable with that. So now, in order to compute the capacity is VMN, well, it's the minimum of VB FCR SX or VMP. Okay. Now, before we start chugging along, can somebody tell me what is VMP for the W14 by 61? Actually, let's put that over here. Okay, 383 what?
Foot kips.
Okay. Okay. So let me show you something. So watch this. So on the top, okay, we have feet. Remind me, what's feet for beams? 0.9. We have our FCR 46.779 KSI. We have SX, which is 92.1 inches to the third. And then we have 383 foot kips. Anybody see a problem?
Top's going to be in inches.
The top's going to be an inch kip. So what we need to do is we need to say, we need to convert that. We need to convert that by dividing by 12. So what do we get for that top?
I got 323.13 here.
323.1.
0.13.
Do I have a second?
Yeah.
So that's our capacity. Because we're taking the minimum. So again, CV served to elevate the capacity, but not beyond MP. The VMN. What is that? So let me take a step back and see if anybody has any questions about that. I know that calculation is a little bit more involved than you're probably expected, or you probably expected. And again, there's not a, how can I put this? Not really a very good shortcut for this. You just kind of have to check through it. So. Sound good? Okay. Now, I want to introduce you to the concept of design, okay, for discretely-braced beams. And in order to do that, I kind of need everybody watching up here. Because I'm about to show you what I think is the craziest looking design aid in steel design. But it is not that intimidating. And I want everybody to kind of recognize that. Okay. Let's take a look at this. This is the LTB curve for steel beams. The problem is that there is a different curve for every beam. So for example, I could plot one for a W24 by 76, but if I said, okay, now let's change it to a W14 by 61, now it is a completely different curve. It's the same equations, but you're going to have a different LP and LR for every shape. You're going to have a different BF for every shape. You're going to have a different hyperbola for every shape, and so on and so forth. This is a different problem than what we had with columns. With columns, if you had the slenderness, there was really only one parameter that defined what the curve looked like, and that was Fy. As long as you knew what Fy was, you could use the same column curve for literally every column. You can't do that with beams. For beams, you're going to have a different LTB curve for every beam. So with columns, we needed the capacity tabulated in order to design, but we can't really even tabulate it very well because of this. So how do we design beams if each beam has a different curve? What we do is we use a design chart that has all the curves all plotted together. This is table 310, okay? And it looks like a mess. It looks nasty. It's not. It's actually not as bad as you would think, okay? This is table 310, a little bit about table 310. So first off, this is another one of those bookmark type tables. Everybody ought to open up to it because we're going to have a little quick exercise working on this together. Because this is one of those guys that I think that everybody kind of needs to have some experience with, okay? But yeah, so while you're turning this in, it starts on page 3-92, but the guide goes on for several pages. Let's see. So, but yeah, so as I was saying, so yeah, with the column curve, it was only a function of the slenderness of a shape, whereas for this, it's a function of a lot of other things. Okay, so the way that this works is that on the x-axis, you have your LB, and on the y-axis, you have your plotted capacity. Now notice how there is a scale for ASD and one for LRFD. We're only going to focus on the LRFD numbers. One thing that's worth mentioning is that in order to use this design aid, two things have to be true. Okay, the first thing that has to be true is you have to be dealing with 50 KSI steel, which for W shapes is a very valid assumption. That's not a big deal. Okay, but what is the other thing that has to be true to use this aid? CB has to be 1. Okay, CB is not 1 in every analysis case. And so what we're going to do on Wednesday is so Wednesday and Friday is going to be focusing on how to design discretely braced beams. And the way that I have the lectures discretized is the first lecture is for what I call low CB values, and the second is for high CB values and how that changes the design process. So we'll get into those details on Wednesday and Friday, okay? But this is the guide that we use. Let's talk about how it works. Okay, so I want everybody's eyes up here because I've got some slightly animated slides because I think this will be an easy way of explaining it. So here's how you use the table. Okay, so what you do is, so at the very beginning of a design problem, the first thing that you're doing is some structural analysis, and so you're computing an MU, VU, all that. So the first thing that you do is you take that factored moment and you divide out the effects of CB. So if you're doing a problem and you have a CB value of 1.3, what you do is you compute your factored moment and divide it by 1.3 so that you have a moment that you can go into the table with, okay? And so what you do is you look for the point in your table that corresponds to the x coordinate being LB for whatever problem that you're looking at, and your y-coordinate being that factored moment divided by CB. So, an x-axis, you look at your unbraced length, y-axis, you look at the moment, okay? And what happens is, you then look up and to the right, and you find the first shape that's plotted with the solid line. So let me kind of show you how this works. So, for example, let's say your unbraced length for a given problem is 28 feet, and let's just say that your MU over CB is 1162. I just made these numbers up. What happens is, you look up here, what happens is you find that point, so that's this point right here. So this is an unbraced length of 20 feet, and the factored moment, you can see it's about 1162. And what you do from there is you look at this region, okay? This region, the reason that you're looking up here is because every shape that's in this region, okay, is a shape that has a higher moment capacity and a longer unbraced length. So these would be safe sections to select. Like what we couldn't do is find this point and start picking shapes down here because they don't have enough capacity, right? Does that make sense? Okay, so what you then do is you look up and to the right and you find the first solid line. Now, why do you find the first solid line? Well, look right up here. I want to take a look at these shapes. So look at this. This is a W18 by 175. This is a W40 by 167, and this is a W27 by 146. Of these three shapes, why do you think this one's solid and these are dashed? It's the lightest. That's exactly right. So the way that table 310 works is within a given region, the solid lines are the ones that are the lightest within a given region, okay? So what you would do is you would go into here and you would say try a W27 by 146. That would be the section that you would select for trial purposes. Now I say trial purposes because probably the most important aspect of dealing with table 310 is that you're dividing out the effects of CB. And as we're going to see throughout this week, that can lead to some problematic choices. And so that's what happens when we have quote-unquote high CB values, is that we can get some false positives. And we'll see that in the pre-recorded lecture on Friday, but I kind of wanted you to see how this works. What I want to do today for the rest, and this is, I'll probably end up letting you out a little bit early after this, is I want to, what I want to do is make sure that everybody's comfortable with this. So all I want you to do right now is I want you to help me out. LB is 14 feet. MU is 2150. Find me the section that works. And I'm here, so if you have any questions, like, this is what we're here to do. And one thing I will say that you kind of have to get a little used to is reading the labels. Sometimes it can be a little tricky with this aid, and there's sort of no real way around that. I will turn to the same page and see. So I'm curious, does anybody have a shape?
A W40 by 167.
The W40 by 167. Everybody else have that? You have that? Okay, good. Now, one thing that you can do if the labels were a little hard to read is if you notice that W40 by 167 curve, that W40 by 167 curve, you can trail it upwards, and that label shows up twice. Okay, so that's something that you ought to look into. Okay. Now I have another thing I want to show you before we close up for today, but I want to stop for a second, see if anybody has any questions just sort of navigating this chart. It looks like a nightmare the first time that you see it. It's not so bad after that. So far so good? Okay, I want to show you all something, and I don't normally bring this up, but I kind of want to show you this because I want you to understand what you're getting on the exam. And by the exam, I'm referring to the FE exam, okay? So, I think that, let me see. So, I think this will probably be it. Yeah, here we go. So this is the reference handbook that you get on the FE exam. I think this might be a slightly older edition, but for the sake of discussion, this is good enough. So how many of you have ever looked at this before? Good. If you haven't, you should. This is the reference handbook that you're allowed to use on the FE exam when you take the test. Now, I'll be honest, a lot of students say, oh, I don't need to look at it because it's a searchable PDF and I can just hit Control F. But I do think it's a good idea to at least sort of orient yourself to what's in it. I'm not saying you need to memorize it, but at least knowing what's there and what's not, I think will definitely help you out. And I think that we're at a good spot now that we could probably look at the steel design portion to actually show you what it looks like. So the way the book is structured, you have the stuff that's sort of general to everybody, and then you get into individual content for each major. So there's chemical engineering, civil, environmental, etc. Let's look at the civil engineering section. So if you look at the civil engineering section, first off, some of this stuff probably is a little familiar, right? Air, water, and solids, right? What's the weight of the air? The weight of the air is 0, right? You remember that stuff? Porosity. You're like, we were having a good day. No, I'm just kidding. No, I love soils. But so we get into coefficient of uniformity, and then we get into consolidation. We get into time factors with consolidation. I'm not sure if you cover this in soils or you cover this maybe in a foundations class, because it can get a little, I'm not sure where that is. More Coulomb failure criterion, lateral stress, soil classification. Here's AASHTO, here's ASTM. Okay, my neck of the woods, structural analysis. So a little bit on influence lines and then truss deflection. Y'all remember that stuff, right? It's written a little differently, but remember how we had a little f, big F, L over EA, and we sum all that to get the deflection in a truss. So yeah, it's written a little different, but it's not all that bad. Like we did that before in structural analysis. See, this stuff's given to you. All right. We have a little bit of stuff on indeterminate analysis. This is on determinacy, whether or not structures are indeterminate, unstable. Again, written a little differently, but it's all the same stuff. Okay, now we're starting to get a little bit closer to our neck of the woods here in steel design. So the first thing you'll see is all our load combinations for LRFD. You see some stuff on roof loads and wind loads, but we really don't, it doesn't get too hairy on the exam. Concrete design I will skip, but for those of you that have had concrete design, some of this stuff is probably pretty familiar. Like you've probably seen these before, you've probably seen beam column charts. Okay, let's get into steel design. Now we're in the land of our specific class. So the first thing they show you is the yielding equations, and then we have lateral torsional bucklings. Like for example, here's our CB chart. Columns, so you can see, you know, we used all that stuff in here. Here's the CB chart that you all have been using this semester, right? That's all present in the manual. Tension members, so we have net area, we have effective net area and all that. Okay, what actual design data do they give us? So one thing they give you is some snippets of W sections. They'll list the area, the flange depth, or sorry, the web depth, the flange properties, the moment of inertia. They don't give you everything, they give you enough that you need on the exam. So what you will see in here is the data that you need to negotiate steel design, but it's much more abridged than what you find in the manual. Okay, what's the next thing they give you? Look at this. ZX charts. They're that important, okay? You desperately need them on the exam. Notice how they're grouped in the same way. The one thing that I think is noteworthy is that there's no there's no ASD. There's no green numbers and blue numbers. They just use LRFD. So you just see the PMP, the PMR, the PBF. You don't see the MP over omega, the green numbers. They're all gone, okay? Let's see.
Do you think in future manual editions the ASD will just be gone?
Sorry, say that again?
Do you think the ASD will ever be gone from the manual?
Ooh, that's a good question. I'd be all right with that. I really would. And the reason why I'd be all right with that is not because of some personal preference towards one philosophy or the other. To be honest, LRFD is harder. It is more difficult. The reason that I prefer it is because the concrete industry has said that's the only way that we're doing it. In AASHTO bridge design, that's the only way that you can do it. Steel is one of the few lingering, even the timber design spec now has LRFD. While they have ASD as well, they're even moving down that road. Steel is one of the few industries that sort of lagged behind, and the reason they've lagged behind is because there's a lot of folks out there that have been using ASD this whole time and don't really want to change. Do I think that LRFD will go away, or ASD will go away? Yes. I think it'll take some time. So, okay, these are the charts that you saw here. They only include one page. So notice how they only include one page of ZX charts. They only include one page of the beam capacity charts. But you can see it's formatted the same way. They include the K values. We didn't use this semester, but you should be able to, you'd be just fine with these. This is just another way for computing K. We didn't use this chart for computing the K or the VF critical for columns because we just computed it directly. But we did use this. This is the table 4.1 where it lists the capacity per lane. It just looks a lot different because there's no ASD and LRFD numbers. It's just LRFD. So if we have a W14 section that's 14 foot long, we can find a shape, a 12 section, a 10 section. Again, they didn't include everything, just enough to be able to negotiate these sections of the manual. And you can go past it. There's also a lot of other cool stuff in here about hydrology and transpo and surveying and curves and horizontal and vertical curves, all that stuff that I have looked at a long time, but you all looked at probably yesterday. So, but yeah, I do think it's worth sort of mentioning. But the point that I've been making is that the stuff that I've been trying to show you is the stuff that you need on the in order to do steel design. But also, I want to make sure that you're learning methods that are also present on the exam. So yeah. So everybody comfortable with table 310? All right. So here's what we're going to do. On Wednesday, we're going to actually start doing some discretely braced beam design. On Wednesday, we are doing CB. We are doing design for what I'm calling low CB value design. And what I mean by low CB values is that we will not require a whole lot of iteration. High CB values, we will. And there's no real way around that. You'll see what I mean when we get to it. But if you're comfortable with table 310, you're comfortable with everything we've done so far, then discretely braced beam design won't be all that hard. I'm letting you out 9 minutes early. That's all I got. I will see you all on Wednesday.